Hello, I'm David Cadron. This picture shows fresh core for unconsolidated sand reservoir. It is a slurry of loose sand and foamy viscous oil. As fluid is produced, reservoir sand grains positions are altered. Beside an inflow of sand, near wellbore permeability and porosity change, contributing to flow rates greater than flow theory predicts. Because of experience with sand inflow in perforated vertical wells, horizontal wells were equipped with slotted liners to block sand inflow. Blocking sand inflow causes a steep production rate decline that later becomes more shallow due to oil seeping through the blocked sand. Sand inflow increases oil rate and sustains it for years. Perforating slotted liners and operating a well in ways that manage sand inflow increases oil recovery. Slotted liners are designed to facilitate coarser sand grains forming a matrix over a slot, trapping smaller sand grains and solids in the matrix. When the matrix is full of smaller materials, a filter cake is formed that severely impedes viscous oil flow. How thick is the filter cake? Stating this in terms of filtration process, for every cubic meter of oil passing through the liner, 2.3 cubic meters of sand residue accumulates outside the liner. To illustrate the impact of this process, in this horizontal well, compacted sand accumulation around the liner is about 6 meters thick over the length of the wellbore. Perforating slotted liners in vertical wells increases rate after the initial influx of sand is removed. Maximizing overall profitability from perforating a slotted liner requires addressing these four issues. Production rate in the liner is too slow to transport sand. How much of the liner needs to be perforated? How much sand needs to be removed? Are there less expensive, secure methods of sand disposal? Perforated vertical wells provide information on unconsolidated sand reservoir characteristics and behaviors that will help address these issues. To address the issue of removing sand from the liner, this can be accomplished by continuous fluid loading at the required fluid velocity or by recent innovations in sand cleanouts using jet pumps. Shot density, perforation interval spacing, and drawdown steps provides an operator with the means to manage sand inflow rate and volume. Successful fluid loading requires a dedicated load fluid pump for continuous injection at a rate required to achieve sand transport velocity, in addition to a production pump with the capacity to produce load fluid and sand, plus effect drawdown on the well. There are diminishing returns in perforating too much liner in terms of the costs of perforating and the volume of sand handled versus oil volume recovered. Perforating to create a continuous sand-free cavity from toe to heel would generate an order of magnitude more sand. High-pressure slurry injection and gravity feed injection into unconsolidated sand reservoirs are proven environmentally secure, lower-cost sand disposal methods. In conclusion, flow into a slotted liner is blocked by an accumulation of compacted sand several meters thick. Large diameter perforations are necessary for extraction of the compacted sand. Perforation spacing is at the operator's discretion based on diminishing returns of oil recovered and volume of sand that will be handled. The need for sand removal from the liner is short-lived. Novel technologies with proven track records are available now to remove sand from the liner. Jet pumps have features that make them better suited to produce sand-laden heavy oil from horizontal wells. Gravity feed slurry injection and high-pressure slurry injection are proven methods of lower-cost secure sand disposal.